Good morning, everybody. Welcome to the webinar. This time it's about selecting the right flow meters for compressed air and technical gases. And let me share my screen to start the actual presentation. So, selecting the right flow meter for compressed air and technical gases. How can you do this, and what to look for? That's what this webinar is about. My name is Pascal van Putten. I'm the CEO of VPInstruments, and my company offers industrial clients energy management solutions for compressed air, obviously, and also for technical gases and other utilities. And our company has over 20 years of experience in this field of the business. Now, let me ask you a question first. If you were back in 2013 confronted with the choice, invest in Bitcoin, and let's put it this way, invest in 10 Bitcoins or invest in a flow meter. And let's assume that you are an energy manager of a plant with a 250 kW compressed air system running 24/7 a year, all year round. Well, if you would have done that, 10 Bitcoins, or invested in a flow meter and realized 25% energy savings, for example, by leakage management, it would have ended up here today. So, well, you could have been lucky a few months back when Elon Musk was twittering around. Then you could have doubled the amount of energy savings. But right now you can see that the energy savings you would have realized in your compressed air system would have been a little bit higher than the return on investment on those 10 Bitcoins. So what I always preach to our customers and advise to any energy manager, it's always a good investment to work continuously on energy savings. And it could be as simple as investing in a flow meter. Of course, it can also be more complex, that you have to take other measures as well. And why compressed air? Well, compressed air is the third or fourth utility in most production companies, and it's a very expensive resource. It costs about 8 to 10 times more than the electric equivalent of power. And in an average production plant, compressed air is 10 to 30% of the electricity bill. So it's also a very significant part of your energy bill. It's also misunderstood by a lot of users and sometimes misapplied, and therefore it holds a high potential for energy savings. Now, if you zoom a little bit into compressed air, how it's generated, first of all, of course, you need electricity most of the time. Sometimes people use diesel generators or diesel-powered compressors, but most of the cases you have an electric motor, and this will convert the air from the atmosphere into compressed air. And while doing that, about 85% of the energy is lost through heat loss. And it will result in only 15% of useful compressed air. And if you then go further down the road into the plant, you will find out that about 50% of that air is again wasted by leakage, by artificial demand, inappropriate use. And only half of it is basically used for production. So that's a huge loss of energy, and that's why you have to be very careful by applying compressed air, and you have to take good care of your compressed air system. And here's an example of this. This was a project we did in a steel plant where they had a big project to save energy on all kinds of utilities, one of them being compressed air. And what we found there is there were huge leakages underground in old parts of the plant, but also air was misapplied in things like cooling of material, where they could also use low pressure air generated by blowers. So here a complete monitoring system was installed, and basically was the basis for a big energy savings program, which resulted in the end in a return on investment of less than half a year, and it was in a multiple of hundreds of thousands of dollars. So it was a very significant energy saving. The other part, technical gases, which are also used a lot in production plants, are also a very interesting thing to look at. And why? Because they are even more expensive if you compare them to compressed air costs. Look, for example, to nitrogen, which is already about 20 times more expensive. Or if you look at helium, it's even more. So measuring those gases, not only by just measuring the pressure at the cylinder when it's empty, but really measuring the flow going to different departments can be very rewarding. And in a lot of cases, you will find equipment turned on while it could be shut off, or you will find small leakages of nitrogen, etc. So, and let me illustrate this by the next case, which was in an automotive plant, where they use a lot of argon for welding. And in this case, all this argon was basically generated on site, as you can see on the picture. And then it was moved towards the machines through pipes, which was still okay. But at the machine level, there were a lot of welding robots with rubber hoses. And those hoses were probably 20 plus years old. So they had a lot of small cracks in it because of all the movement of the robots, of course. And they found out that by fixing those leaks, you cannot fix them all overnight, but eventually they could save $80,000. And not only on the argon consumption, there was also a side effect that the trucks that would deliver the liquid argon, they would have they could come less often, not maybe twice a week, but maybe once per 2 weeks, for example. So it also saved on that part of their carbon footprint. So it's basically like an X-ray that a doctor uses. A flow meter can reveal things that you normally don't see if you look at a pipe. And similar to a doctor performing an X-ray, a flow meter can also have some other benefits. And you can think of not only the leakage you might find or the reduction of consumption, it will also help you to achieve your carbon reduction goals. And we also have seen cases where flow measurement helped people to optimize the performance of machines or the performance of a production process. Also, by having flow meters installed, you can finally make data-driven decisions when doing another investment. It's not about guessing. You have real solid data where you can say, okay, this is so many euros per year or so many euros per month. So it's worth our investment to fix this. Also, we have seen cases where fixing leaks and reducing consumption resulted in an increase in production capacity because the leaks were so big that the machine was basically underperforming. And last but not least, it's also about compliance. So flow meters are often used to supply the data for ISO 50001 type certification programs, also for energy rebate programs. So it's also for that part important to have reliable data, and flow meters can deliver you that. Now, there are a lot of technologies available to measure compressed air or technical gas flow. There's thermal, vortex, there's orifice plates or differential pressure-based flow meters, Coriolis, turbine or mechanical rotary displacement meters, and there's clamp-on ultrasound. And in the next few slides, I will show you where you could apply those technologies and where they would be performing at their best, and also some examples of where not to apply these. Let's start with thermal. As a manufacturer of thermal sensors, yeah, we highly recommend them, of course, but you also see that they are really performing well in mainly in the main header where the air is dry, to measure, for example, the airflow going into the plant or into various departments in different buildings. You can use them for cost allocation, and they're excellent for measuring leakage flow. And I will come back to that also later in some slides further down this presentation. If you go to the point of use, say the machines, you also can use thermal mass flow sensors. They're also very good to measure demand side. There you would find more the inline types, which means that you have to mount the flow meter inline in the pipe. And there you can use them for also for leakage management in the machine, to benchmark machines, to allocate costs, but also, for example, to size nozzles or to select the right nozzle for a specific production process, for cooling, for example. And last but not least, also for process control or for gas mixing, you will find thermal mass flow sensors. Coriolis meters are, I would say, yeah, one of the best technologies, probably most accurate on the market, apart from really the reference meters they would have at the national lab. These flow meters can measure directly the mass flow. Basically, they weigh the air or the liquid, if it's a liquid Coriolis meter. And yeah, gravity and weight, it's all very well defined. So you can basically measure extremely accurate the airflow or the gas flow. So typically we find them in some air over the fence cases where there's a lot of money at stake. For instance, if you have $1 million a year or €1 million a year electricity bill, and this is going into a compressed air project where you buy basically the compressed air, then you want to be very sure that you don't pay too much for the air. Also, you find it sometimes in compressor testing, but it's rare. I've seen them a few times, and as reference meters in sometimes in calibration labs. And why? Because it's a very accurate technology, but it's also a very expensive technology. It's not these things don't come cheap, so that's why you don't see them in the more general purpose applications. Another technology we will find in compressed air is, and also in technical gases, is the clamp-on ultrasonic flow meter, which is very interesting and convenient because you can basically clamp it around the pipe, and it basically sends ultrasonic waves through the gas and picks them up again. And by doing that, it can measure the velocity. And you don't have to drill any hole. So you might think, well, that's very convenient, no drilling. And that's also why you find them a lot in applications where there's no drilling allowed, like certified welded piping, or pharmaceutical, or very high-end electronics manufacturing, semiconductor, or food and beverage. So when you're not allowed to drill any hole, this can be a very interesting technology. Although it has also its downside, and that's that the signal can be lost if the pipe wall is too thick to conduct the signal through the gas and back. So wall thickness in combination with low pressure is not a good combination for this type of technology. Then the good old orifice plates and differential pressure meters. You will find them a lot in old plants, also in the chemical industry. They're used a lot because they are semi-first principle. They're quite straightforward. You take a plate, you drill a hole in it, and if you know the diameter of the hole, then you can basically use a differential pressure device to measure the differential pressure. And then if you look at the theory, you know and you apply the right formulas, you can calculate the flow. So that's why they are around on the planet already for a very long time. And you still find them a lot in compressed air testing applications, like if you need to test an air compressor to write the specification sheet, or if you want to test an air compressor in the field, then you will find this type of sometimes also temporarily differential pressure meters. But I would not recommend them for permanent applications, and that's because of the pressure loss. And I will come back to that later in a slide. The pressure loss can be quite significant, which means that you have to pay more for your energy bill, basically. Now, there are some variations on this, like the cone meter or the Venturi type of flow meters that have a lower pressure loss, but also that comes at a price. So these are more expensive. So where can you use then differential pressure? Also, that is if you use a insertable differential pressure meter, and that's one of the devices we offer as well. It's an insertable probe that uses still the same principle of differential pressure, but then it's more like a pitot tube on an airplane. So it's a smaller probe, so it doesn't block the pipe that much. Pressure loss is lower, and that's a very good tool to trend efficiency of a compressor or to test compressor performance in the field. Although there are restrictions, of course, because it's an insertable probe, so you have to take into account that there can be insulation effects. The advantage of these type of devices is that it's all in one, so it outputs a direct mass flow signal, and you don't have to do all the calculations or programming yourself. It's a complete plug-and-play unit. Now this table gives an overview, and I'm not going to go through all these details right now, but it might be a good reference table for you to look later after this presentation. But I would like to highlight a few things in the next slides where you could look at when selecting a flow meter. First of all is the flow range, also called the dynamic range or the turn-down ratio. This dynamic range can vary a lot depending on the measurement principle you choose. And I chose this thermal versus DP as an example because that are probably the biggest outliers here. Thermal has a huge dynamic range, and it's very sensitive in the low end, as you can also see in the graph here. You see if the flow goes a little bit up, then already the signal starts to rise quickly. While if you look at a differential pressure based flow meter, the flow goes up even at 10 here meters per second. The signal still goes up slightly while the thermal is already here. But the advantage is if the velocity starts to increase and increase and increase, it's just like with riding a bicycle or driving a car. The friction goes square with the velocity. So the signal starts to increase higher and higher and higher when you go higher in flow, which makes it an excellent flow meter for high velocities where the thermal mass in the end will bail out because it cannot basically heat itself anymore, and also the difference in signal will become smaller and smaller and smaller. So that's why we recommend use thermal typically for big range applications from leakage to high flows in one instrument, and use the differential pressure based if you want to measure high flows. For example, if you want to measure directly behind a compressor where the compressor turn down is also not very big. Another thing to look at besides flow range is also the temperature range. Temperature typically for thermal mass flow devices is limited. There are some exceptions to this, but in general you could say that the temperature range is limited to about 60 degrees Celsius, while differential pressure devices, it's basically a piece of metal in the pipe, so it can go much higher. And last but not least, differential pressure is also much more suitable for wet air. The small drops in the air or the mist doesn't really hurt the signal. While if you have a thermal device, if it would be hit by a drop of water, then you will get a spike in your signal. So that's also why you'll find differential pressure being used directly in a wet air application, for example, in the discharge pipe of a compressor. Now, another thing to look at when selecting a flow meter is if it's a mass flow meter, and preferably also a multivariable flow meter, which means it also has a built-in pressure sensor and temperature sensor that you can also read out. So in that way, you have flow, pressure, and temperature combined in one instrument, which is by some directives like ISO 11011 also mandatory if you do an audit. So why not combine it in one instrument? But also it can be very helpful to find pressure and flow combination problems. Like if the flow will be high, pressure drops, and that might reveal that you have an issue, for example, with your pipe network. And that can lead to interesting discoveries, like maybe some user is using way too much air that basically sucks out all the air of the pipe, and then another machine will trip because it has not enough air anymore, not enough pressure. So we have found a lot of problems with this, and that's why we also standardized on having flow, pressure, and temperature in one device. And temperature can also be interesting if you measure flow and temperature, for example, downstream of an air treatment equipment like a compressed air dryer. If temperature rises, that can be an indication that also the dew point will be affected. It can also be an indication that the cooling system is fault internally. So it helps you also to identify maintenance-related issues. Meter run is also very important. If you look at the different flow meter technologies, you will see that the meter run they need varies per technology. And nowadays, a lot of insertable flow meters are used. So this is an example that is very well applicable to an insertable flow meter, or to an ultrasound flow meter, which also has a single path where it only sees basically the middle point of the pipe, the middle. And if you would install a flow meter in that, and basically it calculates the average velocity from that spot velocity in the middle. So if you would mount it very close to a source of distortion, in this example it's an elbow, and you would mount it here at say 5 diameters away from the elbow, so that's about here, then the air profile, the flow profile is not very symmetric. So the flow sensor will show maybe a lower value, sometimes a higher value than the average flow. And that effect can really be dramatic. In some cases, you will find 30% error if you are, for example, close to a butterfly valve or to a very close to a diameter change. So it's important to respect the guidelines which are provided in the user manuals. And even better, from my experience, I would say stay away longer if you can. The farther you are away from the point of distortion, the more symmetric the flow profile becomes, and that's also the more identical to the way the flow meter has been calibrated. Another thing to look at is air quality. I already pointed out the difference between differential pressure and thermal mass, but there's something else that's severe pollution. That could be oil, that could be rust, it could be something out of the production, like in the picture below, it's probably grease, or maybe we also had cases in factories where they made mayonnaise from vegetable oil, and then the pipes would be filled with mayonnaise or something similar to mayonnaise. And you don't want your flow meter basically to be hit by any particles or to be covered with oil and that kind of stuff. So what we advise is always take a sample of the air by opening a valve before you insert anything, and just check the air quality visually by take a piece of cloth or something to put over the opening and see if it becomes brown, or see if there are any flakes coming out. But watch, of course, your eyes and put on a protective piece of eyewear. And then if you see that there are occasionally particles, you can consider to use a cone strainer like in the picture below to protect your flow meter from those particles. So it will be protected and it has a longer lifetime. Now, if you decide to go into the wet air applications, then it's important to avoid excess water. And in this example, you see one of our insertion probes, which can be used for wet air, but it cannot be used as a water flow meter. So you should stay away from the lowest point where water could collect. It's also recommended to stay away from vertical installation, because then the water might drip down on the probe and it could also cause issues. Actually, the best way to install this is in the highest point and then under an angle of say 30 degrees in a horizontal pipe. And even better is to move away from the whole generation part and stay behind the wet receiver, because then most of the water is already separated, and then you can mount the flow meter here, where you would also only have occasional water hitting the flow meter. In some applications, you will find bidirectional flow issues, and we've seen that a lot in bigger networks where there are multiple compressed air stations that generate the compressed air. but also where you have users downstream with their own individual point of views receiver tanks. So what can happen in that case is that the flow meter at one point shows consumption, and then at some point when the machine is turned off, it still shows some consumption if you would have a unidirectional flow meter. And then if you would basically integrate this and calculate the totalized flow, you will end up with a higher number, like for example 1,000 cubic meters. But then if you would have mounted a bidirectional flow meter, then it would have revealed that this flow, which is not in this direction, but actually in this direction, so basically the flow goes back from the tank into the network, which means that the machine at that point was not consuming a total of 1,000, but it was delivering also some air back to the network from the point of use tank. And we have seen this in factories with ring networks. We have seen this in factories with multiple compressor houses, and also in factories where they have all these distributed point of use tanks. And that's where we recommend to use a bidirectional flow meter. And this feature is available in our products. Sometimes people use a flow switch externally. It's also a possibility, but it's easier to have it all combined in one device, so it can do the calculation for you. And one more thing about before you select a flow meter, I also recommend always to gather all the process data you can. So it's about the type of gas, it's about the flow range you want to measure, it's about the pressure range to which the flow meter will be exposed, temperature range, air quality, and last but not least also the pipe diameter. And while you're checking this in your plant, it's also good already to make pictures of those installation locations and see if the required length is available to install the flow meter. If you want to dive a little bit deeper, we have a complete checklist, which you can find also in one of the offers in this presentation. You can also use the QR code or just type in this URL, and that can help you to select the right flow meter for your application. Accuracy. Accuracy is also a thing that is a lot discussed when selecting a flow meter. But accuracy comes with a price. Similar to you have simple cars, you have sports cars, you have very high-end luxury cars. Accuracy, high accurate product will be also more expensive most of the time than a lower accuracy product. But sometimes a lower accuracy product is fine. It really depends on what you want to achieve with your application. Because it depends on how many euros per year, for example, are flowing through your pipe. Is there a lot at stake, like in the example I gave from the air over the fence? If you have $1 million at stake or €1 million, yeah, then you want to have a very accurate flow meter. But if it's a lower amount, or if it's point of use, then sometimes you can deal with a lower accuracy. Also, it's very important to realize that there is something like lab accuracy or calibration accuracy, and there's field accuracy. And typically, if you use an insertable type of flow meter or a clamp-on ultrasound meter, because of all the errors you can make during installation, the practical accuracy in the field might be around 5%, maybe a little bit better. But very good installation is really key to get this accuracy. And we have seen cases where people had mounted the flow meter directly almost in a 90-degree elbow or just behind some kind of distortion element. And then you might end up 50% error. So it's really important to take a look at the installation location. But yeah, the accuracy should also match your application. So if you want to just trend leakages, you can also say, well, just install a simple flow meter and then basically compare the situation as it is now and compare it with the situation as it is after repair and just take that as a sort of baseline. So then the absolute accuracy is not really important. Compressor testing or air over the fence, of course, then you need higher accuracy. And for compressor testing, you could look at ISO 1217 that will specify the accuracy in a relation to the power rating of the machine. Another thing to look at, if you have a very accurate device, you need to recalibrate it. So you should take that also into account when looking at the total cost of ownership. And the other thing, combined errors. So be aware of impact of insulation, but also impact of pulsations in the airflow, rapidly changing flows, temperature sweeps. There can be a lot of things that can also add additional error to your measurement. Let's zoom in a little bit more into total cost of ownership. So, of course, you have the purchase price of the flow meter, and a simple flow meter might cost, whatever, 500 euros, and a very expensive one could be 10,000 euros. Another thing to look at also is the permanent pressure loss. So I will show an example of this in one of the next slides. Installation costs, an insertable flow meter. Well, if I put it in a ranking, of course, the cheapest one is a ultrasound clamp on, because then you don't have to drill a hole. You might think, well, you might spend more hours on site to get it working. And then you have an insertable probe, which is quite easy. You have to drill only one hole. And then the most expensive is an inline meter in some cases. If you have a big pipe, especially when you have a large diameter pipe, then it will cost a lot of time to basically mount the inline meter in between flanges. And then there's the maintenance part. So the recalibration costs and maybe other costs you need to maintain the flow meter. All those things I think you should take into account when selecting your next flow meter for your project. And then there is the justification for your investment. And this table I like to use in that case. If you, for example, take compressed air, and you take let's take a 2-inch example in the middle of this table, then the maximum flow through that 2-inch pipe would be typically 1,000 cubic meters per hour. That's already quite high, but let's take this as a good example. That air that might cost you around 2 cents per cubic meter. So if you multiply all this together with the running hours, you will end up with an energy bill related to that compressed air of 80,000. So most studies will tell you that you can save at least 10% on that 80,000 by just by monitoring. And I put a little bit more conservative number here, 5%. So that means that if you want to have a return on investment on this flow meter, you could spend around 4,000 on this, and then it's still a good investment that will be returned in about 1 year. So this can be very helpful to put things into perspective. Now, the thing that is often overlooked is the total pressure loss, and I already mentioned it in my LinkedIn post a few weeks ago. If you use an orifice meter, it will have permanent pressure loss, and as most of you might know, that if you have a compressed air system running at 7 bars, and you could reduce the pressure with 1 bar, or in the imperial world, if you would have a 100 psi system, it's almost the same, and you would reduce the pressure with 2 psi, you can save energy, and that energy will return every year again in savings. Now, if you would take a flow meter, for example, an orifice meter, or also a vortex meter, which often needs a narrowed pipe to increase the speed, then that would result in your compressor running at a higher pressure than needed, because your factory still wants, whatever, 6 bars, 6.5, so your compressor will then run at a higher pressure than the desired pressure. And again, this is a calculation example. Let's take a 50,000 euro per year energy bill. If you would then take an orifice meter with a differential pressure transmitter that needs 500 millibar full scale. Of course, you have also better meters on the market that can deal with a lower differential pressure. But this is an example. We have found these examples also in the field. Then you might lose around 400 millibars just by permanent pressure loss. And in the end, that will cost you also 1,200 euros per year in addition to your energy bill. So this is something you should take into account especially when using flow meters for compressed air and at the supply side where you still need that high pressure. Then you need to be very careful with selecting technology that has a very low or even almost virtually no pressure loss. And that's why also insertable probes are such an excellent choice for this application. And of course, you could say, ultrasound, that's even better in that case because you don't have any pressure loss. Then that comes at a price. Now let's take also a look at the recurring costs of flow meters, because it's, just talked about pressure loss, but there's also something like recalibration. And again, this depends, of course, on how accurate you want to measure and how accurate you want to stay with your measurement. But typically a recalibration of a flow meter will cost you around 500. But that's not all, because you also need to go on site, get the flow meter out, ship it back, pay customs fees. And we identified this issue a few years ago, and we thought, okay, maybe there's a better way to do this. Why not make the flow meter like a printer where you could simply exchange the sensor? Because that would basically slash out one visit to the site. You only have to come there once. But also the flow meter becomes much more compact, so it saves you also on shipping costs, and it's a lower value item, so it also saves you on the customs fees. So that's what we did, and we created this sensor cartridge principle, which is available in our FlowScope M product. That's a very convenient way to recalibrate. It's basically swapping the sensor, and so that's why we recommend this, especially when you are abroad and you deal with a lot of customs issues when importing products from our country, from Europe. So to conclude my presentation, flow meters are a crucial part to help to achieve significant cost savings in your company, but you have to be aware that the technology should match the application. And each technology has its own benefits and its own restrictions. So it's not like there is a golden rule that you should always use thermal, or you should always use differential pressure, or always use whatever. Make your choice based on your application, and it should match really the process and the application you have. One very important thing is always check the flow range and the flow rangeability. If you want to measure leaks, you need an instrument with a big rangeability, because otherwise it will show 0 at some point, and while there still might be very significant leaks. Also, something to remind is that accuracy comes with a price. High accuracy means a highly priced meter, also with more maintenance costs. Another thing to be aware of is take proper care of installation, and check also the total cost of ownership, maintenance, annual recalibration, and all other costs involved with with using your flow meter. So thank you for attending. I guess there might be some questions in the Q&A, which I will be happy to answer in the next 15 minutes or so. So the first question I see is how can you detect leaks with a flow meter? Well, you need two things. First of all, you need a flow meter that has the appropriate range, as I explained in the presentation. So it needs to be have the right range to measure those leaks. And secondly, you want to correlate the airflow in the plant to the production hours. So you need an energy management solution that's ideal, an energy management software solution that can correlate the working hours to basically to the airflow. But sometimes it's really obvious. If you see, for example, the coffee breaks or the lunch breaks in smaller plants where they basically go from their workplace and go to the canteen, you can already see that the flow goes down. Or if you look in the weekends, you can sometimes see also that on Saturday there's no production, and then you instantaneously can see how much air is flowing, and then simply divide that on the nominal flow, and you know your leakage percentage. Another question, in case of bidirectional flow, should we consider a non-return valve? Yeah, that's a good one. I mean, if you're not interested to see that, and your process allows to do this, yeah, then you could say install a non-return valve, and then you don't have to bother anymore about the reverse flow. It's, by the way, interesting. I have seen cases in a compressor where the non-return valve was broken, and then the flow meter was able to reveal basically that there was a broken non-return valve. So it can also be a way to keep an eye on those valves. But yeah, that's a way. If you don't want to see it, you could mount a non-return valve, and then you're sure that the flow doesn't go backwards. The 30-degree angle installation by Bernd Losberg. Why is it so important? I could try to illustrate it here with my pencil, but then it's basically if your probe is like this or like this, and there would be a drop of water on the probe. If it would be in this position, it would basically drip down, and we have seen cases where the drop would basically come in front of the thermal flow sensor, or in front of the pitot tube differential pressure sensor. Now, if it's mounted like this, thanks to gravity, the drop basically moves down to on the lower side of the probe, and basically it drips off. So it's a very simple way to keep water, oil, and other dirt off the probe, and that's why we prefer this 30-degree or 45-degree installation angle. Then I see another question about the type of outputs we offer. In general, on our products, we offer standard Modbus through RS-45, 4 to 20 milliamp as an analog output signal, pulse output, and in the newer products also Ethernet. And you see similar outputs on other devices. Some are only 4 to 20, which I think is sometimes not enough, especially if you have a product that provides also pressure and temperature output. If you want to connect a flow meter to a modern BMS or a modern energy management software solution, then I would go for flow meters with RS-45 or Modbus TCP, which we all offer. Any other questions? Or is that it? If there's anything you want to discuss on a project, oh, there's one other. Okay, the working temperature range for fluids. I'm not sure if I understand that question properly. If you mean for fluids like liquids, or the working temperature range for gases. Maybe you can refine your question if possible. I could already, in general, say that if you look at the table I showed you briefly in the presentation, each measurement principle for liquids. Okay, so we ourselves, we don't offer liquid flow meters, but what you will find if you look, for example, into steam flow measurement, which is sometimes liquidish, but it's still steam, of course, or if you look at hot water, then you will see that the flow meter elements are often separated from the electronics if it's a high temperature application. But for the general, we see a lot of MEC meters or mechanical meters even in water flow measurement. The typical temperature range for those is what you have in a normal building. So it's between just above freezing point till 30 degrees or maybe 50 degrees. We don't have much experience with exotic temperature ranges in liquid flow. That's an interesting one. How do you verify the cartridge sensor with the electronics? Actually the cartridges we manufacture, they are actually a complete flow meter. So there is a small memory inside with all the calibration data inside the cartridge. So the electronics are basically reading out those values, and then they know what to do with it. So all the calibration data is contained in the cartridge. Any other question? Maybe one thing I didn't address, I was realizing during this presentation, is if you are measuring technical gases like argon, helium, and so on, you also have to look at conversion factors. So if you have a thermal flow sensor, for example, it will react differently if you would have argon or air or nitrogen because of the thermal conductivity. But if you have a Coriolis meter, it also will be quite hard to, for example, measure helium because of the very low density. A differential pressure meter also has its limitations and conversion factors if you change the gas. So it's important also to pay attention to the specifications when selecting a flow meter for technical gas, if it can deal with that type of gas. In which industry our flow meters are mostly working? We are involved in projects in the steel industry, in the automotive, in glass, in food and beverage, in general manufacturing, metals. So it's really broad. Where we are less active, I would say, is in the heavy petrochemical industry, where, for example, explosion hazard is a thing, or also the requirements for very heavy duty outdoor use are an issue, or when specific outputs are needed. So yeah, that's where we are sort of stay away from. That's also a good one. Can you measure natural gas for a non-custody transfer application? Yeah, we do that in non-ATEX zones. So a typical standard, I would say, glass factory, the production floor itself is not an ATEX zone, or a standard office building application. You could also see gas flowing through maybe to the canteen or to some part of production. If you have some ovens, yeah, you can use natural gas, our inline meters for natural gas flow, and you will use a theoretic conversion factor because we don't calibrate with the real gas if it's natural gas, but it can give you a good indication of which machine is on, how much air is used or how much gas is used by the canteen in relation to the total gas. Or maybe if you have a big bakery or an industrial bakery, which production line is turned on when, and is it turned off on time, or is it maybe still on with gas flowing but there is no flame, that kind of things. So yeah, you can use it. Hydrogen flow, how to measure that? Yeah, you see in hydrogen flow thermal mass as one of the technologies being used. Also for the ultra high pressures, I believe I've seen also Coriolis, but I'm not completely sure about that. Thermal mass flow works, but the restrictions on materials and pressure rating sometimes make our products not the product of choice in that case. So we don't have really experience with hydrogen flow in real life applications at this time. But if you have a very big business case, I'm always interested, of course, to learn more about it. Maybe it's could be of interest to talk in a one-on-one chat. So we have a few more minutes for questions if you have more. And if not, then I would like to thank you all for attending this webinar. And also, maybe if you want to check, there are some files in this webinar you can download, but you can also go to our website after the webinar, of course, to review our products. And feel free to drop an email to us to discuss your application in further in detail, and then we will be happy to help you further. So again, thank you for attending today, and I wish you a very nice day, and I hope that you will realize a lot of energy savings in the future with our help. Thanks a lot, and have a nice day. Bye.